We're asked to find the critical number or numbers of f of x equals negative 3x squared plus 4x minus 2 and determine any relative extrema. Before we determine the critical numbers, we should determine the domain of the function because the critical numbers must be x values in the domain. In this case though, notice how because we have a quadratic function, the domain is all reals. So if we want to give the domain using interval notation, we would say the domain is the open interval from negative infinity to positive infinity. Next, to determine the critical numbers, we determine where the first derivative is equal to 0 or undefined. So let's go ahead and find the first derivative. F prime of x is equal to negative 6x plus 4. Notice how there are no x values where this linear function is undefined, and therefore we find the critical number or numbers by setting f prime of x equal to 0 and solving. Doing this, we get the equation negative 6x plus 4 equals 0. Solving for x, we subtract 4 on both sides, and then divide both sides by negative 6. Simplifying, we have x equals 2/3. So now we know the function has one critical number, which is x equals 2/3. And now to determine any relative extrema, we take the domain, which is all real numbers, and divide it into subintervals using the critical number. So for example, if we have the number line, which represents all real numbers, we plot the critical number as an open point, which is 2/3. Notice how this gives us two subintervals, where the interval on the left is the open interval from negative infinity to 2/3. The interval on the right is the open interval from 2/3 to infinity. And now we're going to pick a test value in each subinterval and then determine the sign of the first derivative. The sign of the first derivative will indicate whether the function is increasing or decreasing over the interval, or possibly constant. And then from there we can determine whether we have any relative extrema. So for the test values, for the first subinterval, let's test x equals 0. And for the second subinterval, let's test x equals 1. So now we need to determine f prime of 0 and f prime of 1. Well, f prime of 0 is equal to negative 6 times 0 plus 4, which is equal to 4, which is greater than 0. This indicates the first derivative is positive over this subinterval. And now we'll determine f prime of 1, which is equal to negative 6 times 1 plus 4, which is negative 2, which is less than 0. The first derivative is negative over this second subinterval. So for the conclusion, because the first derivative is positive over this first subinterval, we know the function is increasing over this subinterval, or going uphill from left to right. And for the second subinterval, the first derivative is negative, and therefore the function is decreasing over this subinterval. So notice how the function changes from increasing to decreasing at x equals 2/3, which results in a high point or a relative maximum. So now we know we have a relative maximum at x equals 2/3. So as a point, we know the x-coordinate is equal to 2/3. Let's go ahead and find the y-coordinate, which is f of 2/3, which will give us the relative maximum. So just be careful here, we're going to sub x equals 2/3 back into the original function. So f of 2/3 equals negative 3 times the square of 2/3 plus 4 times 2/3 minus 2. Simplifying, we have negative 3 over 1 times 4/9 plus 4 over 1 times 2/3 minus, let's write 2 as 2 over 1. Simplifying before multiplying, there's 1 3 and 3 and 3 3s and 9. So here we have negative 4/3 and then plus 8/3 and then minus 2, which is equivalent to 6/3. Negative 4/3 plus 8/3 minus 6/3 is negative 2/3. So now we know the high point on the function is the point 2/3 comma negative 2/3. And this point does represent a relative maximum. So we can say f of x has a relative maximum of the y value of negative 2/3 at x equals 2/3. So again, f of x has a relative maximum of negative 2/3 at x equals positive 2/3. So the relative maximum value is the y value or function value, and the location is the x value. And none of this should come as a surprise. Notice how we have a basic quadratic function where the leading coefficient is negative, which indicates the parabola opens down. And therefore we could have determined the relative maximum by determining the vertex of the parabola, which we did. We just used calculus techniques. And let's go ahead and check this graphically. Here we have the graph of the parabola. Notice how it does open down because the leading coefficient a is negative 3. And the vertex, which also represents the relative maximum, is the point 2/3 comma negative 2/3, which we can see here as a decimal approximation. The parabola also verifies the function changes from increasing to decreasing at x equals 2/3. I hope you found this helpful.